Hi, and welcome to this look at a blast furnace reaction exam question. The question is actually just an application of constructing equations and calculations of moles using large masses. So it tells you iron ore contains iron 3 oxide. That means it's going to have iron 3 ions, iron 3 plus that is. In a blast furnace, the iron 3 oxide reacts with carbon monoxide, which you should know is a gas, to form iron, which obviously you'd expect as a metal to be a solid, and carbon dioxide, which we all know is a gas. So taking that description, you should be able to construct an equation that looks a little bit like that. The iron 3 oxide is going to be based on iron 3 plus ions, and the oxide ion is 2 minus, so the lowest common multiple is going to be 6. So 2 times plus 3 makes 6, and 3 times minus 2 makes 6, hence the Fe2O3 formula. Carbon monoxide, mono means 1, so 1 oxygen there. Carbon dioxide is obviously CO2, and iron, we'll know from the periodic table, is Fe. So in iron 3 oxide, it's an ionic compound, so strong electrostatic attractions between oppositely charged ions would suggest it's going to be solid at room temperature. Carbon monoxide is a very small molecule, so therefore relatively weak intermolecular forces between adjacent molecules, so it's going to be gas. Iron is going to be a solid because it's a metal, and carbon dioxide we know is a gas already, so it should be possible not just to construct the equation but also put the state symbols in. So the next thing to do is look at the balancing. So personally what I say to people is to go for the most complex looking formula there, and that will have the most influence elsewhere in terms of balancing numbers. So in this case it's Fe2O3. So the first thing we can fix is the iron, because you can clearly see iron on its own is only going to be itself. It's not going to influence anything else. It doesn't carry any oxygens or sulfurs or anything other than just Fe. So that's easy to sort out initially. So looking at the oxygens, you have 4 oxygens on the left-hand side. So the only way to fix that problem is by doubling the carbon dioxide on the right. So we solve one problem and unfortunately introduce another. So the carbons now don't balance. We need to think about how to deal with this. I would suggest probably leave this alone, firstly because it doesn't contain carbon in it, and secondly because, like we said, it's got the largest influence elsewhere in the equation. So a little bit of playing around here. Let's add one more CO2 on the right hand side. So that gives us 3 carbons and 6 oxygens. So you've already got 3 oxygens on the left hand side, so why not put 3 carbon monoxides like that? And now we've solved the problem. The equation is balanced. The next part of the question is all about mole calculations, except they give you the data in tons. So you need to remember that 1 ton is actually 1,000,000 grams, remembering that all mole calculations involve grams. Excuse me. So I use a technique called data moles equation moles answer to help me park my thinking as I go. So I'm going to show you how it works for this one. So the one piece of data I have is that I've got 10,000 tons of Fe2O3. That equates to 10 to the power of 10 grams, because I multiply 10,000 times 10 to the power of 6. So 10 to the power of 6 is the number of grams, 1 million in other words, in 1 ton. So consulting the periodic table, I can now work out the moles of that compound. So I take 10 to the power of 10 and I divide it by 159.6. Checking my calculator there. And that gives me 62,656,641 moles. Very large number. Instantly people are going to think, hang on a second, this seems too large. If you follow the courage of your convictions and follow your maths, you'll realize that because we're dealing in tons and moles are worked out using grams, you're almost certainly going to be dealing with millions of moles, because there are millions of grams, or 1 million grams in a ton. So sticking with that, we then look at the equation. So we're interested in how much iron is produced. So the relationship between Fe2O3 and Fe, the mole ratio is 1 to 2. So all you have to do is double the number of moles of Fe2O3 to get the number of moles of Fe metal. So this is the number we end up with. And then finally, to get the answer, you plug it into the moles equals mass over molar mass equation. So you multiply that number by 55.8, and that gives you this great big number at the bottom, which ends up being 6.99. I'm leaving the 2 dots there because 6.99 ... is my calculator value, times 10 to the power of 9 essentially is 6,992 tons. Okay, thanks for listening. Until next time, see you soon.